Hey there, it's your old pal, Mr. Cook. You know what? Let's finish up this review. What do you say? We got three more problems to go. We don't have a lot of space for number 15, so I'm going to erase some of this stuff just in case, because it looks like I've got to do a second derivative there. See, because it says d squared y over dx squared, so I need to get y double prime, if you will. So yeah, just to save space, let's just erase some of that stuff. Okay, here we go. But we're doing implicit differentiation because we got x's and y's, and they both have functions around them, x squared, y squared, or they're multiplying, that kind of stuff. Implicit differentiation is the way to go. So all right, let's go ahead and work through it. So the derivative of x squared is going to be 2x. The derivative of y squared is going to be 2y dy dx. And then the derivative of that constant is 0. So if I want to get dy dx all by itself, I would move the other stuff, the 2x to the other side. And then I divide by 2y on both sides. So I get dy over dx is equal to negative 2x over 2y. And since I got to find the second derivative, I'd probably simplify this a little bit. Notice that the 2's divide out, so I just get a negative x over y. There's my first derivative. Now for my second derivative. So my second derivative, d squared y over dx squared, is going to be the following. Well, I have a function over another function, so this is going to be quotient rule. So, I have my high function up here and my low function over here. So I do low d high. So that'd be, all right. And let me group this. Also the negative, I'm going to put it on the x right there, okay? So I don't get any confusion about where the negative is going to go. Is it on the x? Is it on the y? Is it on both of them? It's only on the x value, and that's it, okay? So low d high, so the low function is y, times the derivative of the top function, which is a negative 1, minus high d low, so negative x, times the derivative of the bottom function, y, which would just be dy dx, all over the low part squared, so y squared. And you might remember this from the previous problem, the other time that we had to do a second derivative on implicit differentiation. That dy dx right there, we've already defined it when we found the first derivative. So whenever I see a dy dx, I can replace it with negative x over y, and that's exactly what I'm going to do over here. This becomes negative x over y, and I'm done with my second derivative. There we go, right there. Put a box around it, you're done. All right, let's see, 16. So we've got arcsecant. You know what? We're never going to have to know arcsecant. We said, in class even, focus on arctangent, focus on arcsine. So you know what? I'm going to break from tradition a little bit. I hope that you don't, get all mad at me and stuff, but I'm going to make this into an arctangent, okay? Don't get mad. Stop complaining. I can hear you complaining in there, okay? I know, but we're just going to do one of those, okay? Because those are the ones we told you that you'd have to know. So arctangent. Find the derivative, arctangent of 5x to the second power is equal to the natural log of y. Okay, no big deal. So the arctangent derivative looks something like this. Just from memory, I think it looks something like this. Arctangent of x, if I take the derivative of this function, it's going to be 1 over 1 plus x squared. Okay, something like that. But we don't have just an x, we have a 5x squared. So you better believe it. This is a chain rule problem. So using the chain rule, let's find out what it's going to be. So arctangent is the derivative is 1 over 1 plus the input value squared, so 5x squared, and then times the derivative of the inside. So that's going to be a 5x squared derivative is 10x. And then on the other side, the derivative of natural log of something is 1 over something times its derivative, and the derivative of y is dy dx. So then we've got to get dy dx all by itself. So we can just multiply a y over there. Y times 10x, I guess, over 1 plus 5x to the second power squared equals dy dx. And we can just leave it like that because it's implicit differentiation. So we can have things in terms of y's and x's. There we go. So if it was arcsecant, you just use arcsecant's rule. But I want to focus on one that we told you guys to memorize, tangent. So you're not like, just scared and like, oh my gosh, I'm gonna have to memorize all these ones too. No. We said tangent, arc sine. Stick with those ones, okay? All right. Next up, evaluate. So the limit as h goes to 0. Wait. Hold on a second. The limit as h goes to 0 and then h is in the denominator. Where have I seen that before? It's been a while. Well, a couple days, but maybe that's a while for you guys. I don't know. But this is like the derivative expression, isn't it? F prime of x, the limit definition of a derivative is the limit as h goes to 0 of like a function of x plus h minus a function of x over h. So, hey, look at that. Like, this looks very familiar. So why don't we translate this into what it's really asking us, okay? Like look at this, okay? This part, f of x, is over here, sine of pi thirds. So wait, all right, so that means that like the function that I'm dealing with, f of x, is probably sine of x. And then the x value is pi thirds. And then overall, this thing is the limit definition of a derivative. So what it's asking you to find, you know, just by noticing that this is the limit definition of a derivative, it's asking you to find the derivative of the function sine of x at x equals pi thirds. That's it. So wait a minute. So that's actually really easy. The derivative of sine is just going to be cosine of x. And if I were to plug in pi thirds, the derivative at pi thirds is equal to cosine of pi thirds. Oh no, now I got to remember my unit circle though. But let's see here. Cosine of pi thirds, let's see here. I think that's going to be a half, right? Isn't that right? Yeah, so a half is my answer, and that's it. So the key to number 7 is recognizing, hey, look at that. That's the limit definition of a derivative. And then picking up some clues. Maybe knowing this form right here would be a good idea, possibly, maybe. And then, you know, being able to relate it to an expression already written out for you. Okay, I think that's all the problems, right? Let me double check. I don't want to skip any of them for you. Nope, I think that's all 17 of them. All right, well, you know what? I'm done with this one. It's 6 o'clock. I'm going to head on home, and then I'll upload these videos on Canvas. I hope that you enjoyed this review. I hope that you got something out of it. If you didn't, you can always ask your calc teacher, whether that's me or Mr. Fowling or somebody else. I don't know how long this video is going to be played. Maybe it's in the future where it's I don't know, somebody from that's currently in this class maybe or something. I don't know. That's high hopes, isn't it? Well, whatever. I hope you have a nice night and enjoy studying. Bye-bye. Have a nice day.